Yeah, thank you very much. This is joint work with my supervisor, Holger Dette, and his very good idea. We submitted the paper 3 months ago. I would like you to talk about the motivation first, and mainly give you, I think the most interesting for you are the finite sample properties, but of course I have to give you also the main results. So first of all, as an introductory example, but I guess it's not necessary here, I just have an AR1 process. So the value depends on the past value here and one innovation term. And it is, that one, for example, is weakly stationary, meaning the first order term is constant and also the covariances over time. And they only depend on the lag. If I have a general weakly stationary process, I can, according to the Volt decomposition, view it as a linear process, like a causal linear process, in the sense that it is represented by non-future innovations. And one term, which is called deterministic, I'm not so familiar with it, but at least the idea I have it from it is that it can be basically represented regarding information I have at hand. But let me know, I usually brush it under the carpet because it's more like a technical thing, but maybe you can tell me something about it later. So let's think about that. Basically, we have weakly stationary processes, which can be represented as linear processes. The problem is linear processes have very nice probabilistic properties, but regarding estimations very bad, because these are innovations, I don't observe them. So what we would like to do, we would like to, given a stationary process, we would like to approximate it with past p values. So we would like to approximate a given stationary process with past p of its values, but in such a way that it has to, that a certain measure m, I just call it m for now, it will be clearer in a bit, that it will be below a threshold, because I don't need it to be, I don't need it to be zero, the difference, but at least it should satisfy, let's say, being below 0.1 or something like that. The question is, what kind of measures are reasonable? And what we want to do for a given p and a given delta, which will be clear in a bit, we would like to establish parameter-free distributions of the estimation. So regarding linear predictions, I think one of the biggest papers, as far as I'm aware, is from Akaike. And there is subsequent work in that direction, but not in that context I will show you here. Let me know if you have an idea later. Okay. Some technical assumptions. I assume a linear process of that structure here. Then I assume that the coefficients are not only summable as usual, but so they decay faster than j to the power -2, so they are summable with j here. They are IID and centered, variance 1, and finite fourth moments. Other assumptions are more technical, which I don't want to point out here. I need non-singularity of certain matrices, which will be clear in a bit. And also conditions on certain gradients, because I will use the delta method. And if the gradient would be 0, it would get a problem. So the first measure, which is intuitive, is, of course, the mean squared prediction error. But that does not really help in that sense that it depends on the scale. But what I know from that preliminary measure, that So usually you are interested in the coefficients, but I'm not interested in the coefficients. I'm interested in the difference between the axis and p-past values. So I'm interested in the measure itself. Very old theory, because I have a certain Hilbert space structure, I can rewrite it as the determinants or the quotient of determinants of Gram matrices. In that context here, because I have a stationary process, I have that the GP here is basically the Toeplitz matrix spanned by the leg covariances. Okay, intuitive measures are, this is scale variant, but if I divide by the variance, which basically means p is equal to 0, then I have a scale invariant measure, which I will focus on here. Or I can think about what is the benefit of adding one past value. So this would be that measure here, which we also discuss in the paper, but I will not focus on in this talk here. So our main aim is to test whether using P information is enough in a certain sense. So I'm interested in the measure here. An intuitive estimator for that measure is a plug-in estimate where I basically plug in the autocovariance estimates, or let's say leg H covariance estimates. And I use these covariance estimates, which in my opinion are not intuitive because they are unbiased. But I could imagine that you are aware of that when you work with it, that these are a lot better to work with than using the unbiased ones, because then the spanned matrices of the empirical objects, the matrices which I use, are positive semi-definite. In the other case, they are not. So the biased ones are actually quite helpful to use, the biased estimates. And here you see the main problem of the typical results. 1991, if you have the vector of the autocorreliances from 0 to p, so the legged covariances, I call them, then they are, the estimation error is asymptotically normal, but take a look at the variance here. It's extremely awful to work with that. I have a long one covariance, many parameters I don't know. What shall I do with it? A preliminary result for our context, which would be parameter dependent, is I basically plug in, or I use that result, then I plug in these covariance estimates at the positions in the matrix before. Then I take the quotient. And by using simply the delta method, here, where do I have it? Okay, here's the sigma. By using the delta method for the measure I'm interested in, I get also asymptotic normality, but here I have an even, maybe not, but in most cases, even more complicated asymptotic variance, because here's even a gradient. And this is actually also taking the derivatives of a quotient of determinants, which is not that difficult actually, but still, it depends on the parameters here. So the limiting variance depends on various parameters, which I can estimate, but possibly very complicated to do that. Or I have to truncate, of course, but then I have to make a decision about where do I truncate. So we aim to derive a parameter-free limiting distribution in order to say whether using P information or P past values is actually enough in some sense, instead of using the full structure. So what we do is the following. The basic idea is we derive a process convergence, and then we can use self-normalization based on that. So I define a sequential counterpart of the biased covariance estimates here. Sequential in the sense that here's a lambda reaching from 0 to 1. Then I plug these in my original measure formulation, but at the positions where the original values were, I put in these sequential versions here. And then, looks extremely complicated, but it's very easy why we take a look at the vector valued process now. Because if I'm able to say something about the limiting distribution of that huge vector valued process indexed by lambda, what can I do? I also know by just dividing the last component by the first, I have my original measure. By dividing that one by that one, I get an information about the other measure I just said. How much does it benefit if I add one value more? Okay, so this is the process where the sequential, this is the process of the differences of the original measures to that version here. Just accept that we were able to define or to derive an asymptotic limiting distribution of that process, where sigma is the original Bartlett formula type matrix. This here is a Jacobi matrix, which is basically very similar to the gradient I just showed you. Still, very big problem. Many different parameters I don't know are in the limiting distribution. I don't go into detail with that, but basically what we used weak invariance principles, and then we showed Hadamard differentiability and used the functional delta method in order for that result here. Okay, now if I only take the last parameter or the last position, and I divide by the integral of, so I do self-normalization, this is my self-normalizer here, then this converges to a distribution, or the limiting variance is parameter free, because this is a Brownian motion divided by itself in the sense of that I integrate over the parameters. So for the original measures, we have a parameter-free limiting distribution. This measure is not very interesting because it depends on the scale. But we can also do that for SP. SP was MP divided by M0. So we are able to estimate that parameter-free asymptotically. And we are able to construct a test for the hypothesis if the scale invariant measure is below a certain threshold. Now you can ask yourself, okay, what is actually delta? What can be values of delta? That's a very central question. But actually, it is the same as asking, it's equivalent to asking if the coefficient of determination is greater or equal 1 minus delta, or here, the opposite. And it can only be between 0 and 1. So I know what delta should be, would be a reasonable choice. Let's say, if I would like to describe 90% of the information, then this here should only be 0.1, and here, in that case, you see, okay, yes, it is. We reject the null hypothesis whenever this statistic is below, okay, this is coming from my previous parameter-free asymptotic distribution. And it has asymptotic level alpha. So if I'm below the threshold, then the rejection rate converts to 1. If I'm at the threshold, it converges to alpha, and below, or the other way around, it converges to 0. Okay, this is the main result, but there's also a relationship between the squared partial autocorrelation function and the measure I just showed you before. But maybe you know how to deal with that. How do you get the information of the partial autocorrelation function if you only have the squared? I don't know it, but maybe you have an idea how to do it. So we actually use the Durbin-Levinson representation for the partial autocorrelation function And we also get a self-normalization, a limiting distribution for that, which does not depend on the parameters involved. Finite sample properties. I hope I have a little bit of time left. So what shall I say about that? Here I simulated, I have a linear process with, we have to have in mind that the coefficients have to decay such that they are summable with the factor j in front of it. So here I have a linear process with coefficients decaying like to the power -4. I chose p is equal to 2, 4, and 6 here. The measures slightly change for different p. This is why they change here. In the geometric scenario, geometric decay, the measure is actually almost constant over p. And for n is equal to 10,000, so this here means the significance level. I should be around the significance level when the measure is at delta. By the way, maybe you have a problem to read that plot. What I actually did, and this is usually done for the rejection probabilities, they are different deltas. It's actually not correct to do that because there are 100 different tests, in fact. But for making it easier, I chose different deltas where I showed the rejection probabilities. And another benefit of our model, the Barndorf and Nielsen result for estimating the partial autocorrelation function assumes a known order. And even, this is a problem, but even in the known order scenario, you see that the parameter of the limiting distribution of the variance depends. The variance depends on parameters. That's what I want to say. So in the case that they correctly specify the order, here are the coverage rates and the length of the confidence intervals. And here, PRV stands for pivotal for our scenario. They are better than ours because when you have parameter-free limiting distributions, usually the confidence intervals are slightly longer. But when so these come from autoregressive 2 and 4 processes, and they correctly specified. Here, we simulated information where the data generating process is an autoregressive 6 process. When they think it's 2, the coverage should be around 90%. Here they are far off, 11% points. And here they're a little bit off. And with our methodology, we actually quite cover that reasonably well. Okay, the main takeaway in this work, we covered reasonable measures and pivoting limiting distribution for mean squared prediction errors, but scaled, let's say. We can apply that for R square, for partial autocorrelation functions, and in our paper you can also see how to estimate orders such that the difference of the true to the linear model is actually below the first order such that it's below 10%, for example. We can also, we actually also extended it to the multivariate context for multivariate processes. And also I said that we were able to do that for that measure here. And in the future, I could imagine that we could extend it to the functional time series context, but then we cannot work with determinants anymore. So it has to be another approach. And maybe there's something like, okay, we have a stationarity setting, but what if stationarity is not fulfilled anymore, then I cannot use these results anymore. So I hope that was helpful for you. Thank you for your attention.